Hey everyone, this is a series of 3 videos about these gas laws in physics. This episode is about Guy-Lussac's law. These laws are of interest to a number of people in different occupations that involves aviation, including hot air ballooning, as well as welding, diving, pipe fitting, just to name a few, and occupations involving transporting and transferring compressed gases, whether this transportation takes place by air, by land, or by sea. LNG, for example, is one example. So, potentially millions of people are involved in applying these laws or doing math with these laws. The video's format is fairly straightforward. I'm going to start with a plain language explanation of what the law says, followed by a technical language variant, and I'm going to connect the two together, and this is going to be followed by a mathematical representation of how both the plain language variant or the technical language variant is represented in math. Okay? Because eventually you need to be able to do some math with it, although your line of work might be slightly different, how the law is actually applied. The video ends with 2 sample calculations, one in metric units of measure and the other one in imperial units of measure. Let's get started. Mr. Guy-Lussac is French. It's a hyphenated name. It's one person's name, and Mr. Guy-Lussac's background, where this law comes from, is hot air ballooning. I'm going to put away the hot air balloon representation here, and I'm going to have a different one. On this bicycle, I have here a tire. This is what I'm going to relate Guy-Lussac's law to. So, in plain language variant, Guy-Lussac's law says that when the sun hits the black tire and the tire's temperature increases, when the tire's temperature goes up, the pressure inside the tire is also going to go up. In the winter or at nightfall, whatever way you look at it, as the temperature of the tire goes down, the tire being a container of compressed gas, temperature of the tire goes down, the pressure inside the tire also goes down. So at night and during winter. That's also why the sidewall of the tire, or maybe your owner's manual, somewhere it says tire pressure so many psi or bars or whatever units of measure, so many psi cold. Because in normal operation, when the tire hits the road, due to friction with the road and due to being exposed to sun, the tire heats up in normal operation and the pressure inside will increase. So you are supposed to measure the tire pressure or set the tire pressure cold as it is, because the pressure number relates to cold temperature. So again, in plain language variant, when the temperature of the tire goes up, the pressure inside the pressure vessel, the tire, is also going to go up. When the temperature goes down, the pressure goes down. Okay, that's the plain language variant. I hope this is fairly straightforward. So let's see the technical variant. The technical variant relates to ideal gases, meaning that inside the tire there are no pollen particles, dirt particles, or any kind of contamination, soot, whatever. So it's pure, and the gas has a prescribed, precise, identical, unchanging chemical composition. Never gonna happen. But that's ideal. That's what ideal gas means. And constant volume means that the tire has a fixed volume. Yes, when it goes flat, it collapses a little bit and it increases a little bit, so the tire is not a perfect analogy, but constant volume means that in a welding or a diving gas container, or in first aid, when you have and I don't have an oxygen bottle here, if you have a fixed rigid wall container that doesn't expand like the tire, okay, volume is kept constant. So if you take a welding gas or a bottle of oxygen or a propane tank and put it out in the sun, as the sun hits it, its temperature inside is going to go up, and its pressure inside the propane tank, oxygen bottle, whatever, is going to go up. That's why there is a pressure release valve on propane tanks, so it doesn't overheat and doesn't blow up, or doesn't, the welded seam on the tank is going to burst at one point if the pressure keeps increasing. So that's what's meant by, constant volume. Okay, so it has a fixed rigid sidewall and it doesn't expand like the rubber tire. Okay, that's important. So temperature and pressure are directly proportionate. What directly proportionate means in plain language again is that increase in temperature, and T from this point on consistently in this video, T is gonna mean temperature, and P is gonna mean pressure. Okay, consistently. So when you increase temperature, pressure is gonna increase, and when you decrease the temperature, pressure is gonna decrease. That's what's meant by directly proportionate. All right. Now, notice that it starts with temperature, and the second item is pressure. It all is temperature driven. To a lesser degree, if you increase the pressure inside an oxygen tank, an oxygen bottle, by say adding more gas to it, increase the pressure, its temperature is going to warm up a little bit. When you inflate a tire, when you're using a pump, valves, whatever, will become hot. So it works to a lesser degree the other way around, but it's predominantly driven in this direction how you read it. The temperature is the input that you are manipulating with, and pressure being the result. Pressure is the resultant. Okay, the resultant variable, and temperature is the input variable. Okay, I hope that makes sense. So it's predominantly driven this way. So let's look at the mathematical representation of how this is written down in math language, that when the sun hits the tire on your vehicle, the pressure is going to increase in it. This is how it looks like. It looks nothing like the previous versions. This is the math representation. What's important about it, and I'm not arguing with the textbook, it can be written in a number of different ways. Two ways look like equivalent fractions. This fraction here being equivalent to this fraction, or it can be written in a multiplicative format, where those two numbers multiplied equal to two other numbers that are multiplied. The letters here, T stands for temperature and P stands for pressure, and 1 means condition 1, meaning condition before heat is applied, and T2 meaning after heat was applied. It doesn't have to be after all the heat was applied, or after a whole day in the sun. It can be 10 minutes after, or whatever. It can be any amount of heat applied between T1 and T2. But this is the before, this is the after, at any given point you so choose. Same for pressure. Pressure 1 is the before, or the initial, the starter pressure, and P2 is the resultant pressure, the after. Okay, so there's a before and after, or a start and a finish. That makes sense? So that's what's meant by 1 and 2. Okay, start and finish. So starter temperature, starter pressure, finishing temperature, starter pressure, finishing pressure. That's how this reads. Now, this is not all the variants. For full disclosure, spoiler alert, it's gonna look confusing. You have all of these variants that you could potentially find in a textbook. Just pick one and work with one that works best for your mind. But they are all the same. How? Look at this equivalent fraction. These two equivalent fractions trade place this way. That's what happened here. Or, this is a different trick. The numerator and the denominators traded place this way. I know you can't really do that in normal fractions, but you can here, because these are ratio and proportion, because I mentioned the word directly proportionate, so we're talking about proportionality here. Likewise, because in a multiplication, when you multiply two numbers, the order of operation doesn't matter, so you can switch around these two numbers. I know they are letters, but when these are going to be numbers, you can switch around the two amounts either which way, or you can switch around the left side or the right side, either which way. So that's why these are all the variants. So how do I know that all of these are the same? So let's pick some easy numbers for temperature and pressure and see how this looks. How about 3 for temperature 1? We started at 3 degrees. It doesn't matter if it's 3 degrees Celsius or Fahrenheit or Kelvin or whatever, just 3, just go with it. Temperature 2 is 6, so temperature went up by 3 units, just whatever units. And pressure 1 is 9, why not? And pressure 2 is 18, so temperature goes up, pressure goes up, okay? Now, 3 over 9 is an equivalent fraction, not in its lowest terms, but is a fraction that's equivalent to 6 over 18. Because if you double the numerator, 3 doubled is 6, you double the denominator, 9 becomes 18. So 3 over 9 is an equivalent fraction to 6 over 18. Likewise, on this side here, the numbers appear at different places, but that's not a problem, because this is ratio and proportion. They are not really fractions, but they work like fractions. They look like fractions, but they are not actually fractions. So 3 over 6 is an equivalent fraction to 9 over 18, because if you triple the numerator, you triple the denominator, 3 times 6, 18. So 3 over 6 also not in lowest terms. Lowest terms would be 1 over 2, but that's irrelevant because this is not fraction reduction. This is just working with ratio and proportion. So the amounts are proportional. Do notice that this proportionality means, and this is critical for the calculations or how you memorize these laws, the number ones appear either on a horizontal line consistently or on a vertical line or line up vertically when in the fraction format. When in a multiplicative format, 1 and 2 are side by side, always in all the variants. Let's go back one slide. 1 and 2 are always side by side everywhere. And here the 1s always line up vertically, and here the 1s and 2s line up horizontally, consistently. That's critical for memorizing this. If you work with one of these fraction formats and you put a 1 with a 1 that line up diagonally, your math is never going to work in a million years. This has to be written with these principles in mind. In the fraction format, the 1s and the 2s must line up either horizontally or vertically. So, let's take a look at the calculation sample, how all of this works. In this example of Guy-Lussac's law, let's start with a temperature, initial temperature of 12 degrees. Start with inside the garage, I don't know. Take it out to the sun, now it's 35 degrees. And again, this is a rigid wall container, an imaginary tire that does not expand sideways, so work with me on this one. It's an ideal gas in an ideal container. If the initial pressure in the tire is 41 psi, what's going to be the resultant pressure when the sun hits it? Okay, I hope that context makes sense. So pick one of the formulas that you like, any, just pick one. I picked that one, why not? And you need to replace the letters here with numbers that are given in that example there. When you do so, 3 of the letters will be replaced by numbers, and there's going to be a 4th letter remaining. What you do is you cross multiply 2 numbers that line up on a diagonal. 2 of them will line up somewhere. Multiply them in any order you like, because multiplication is of this kind that you can change the numbers. It's going to be the same, and divide by a 3rd number. You're going to see on your calculator 119.5. You can round it to your heart's content. How about round it to 1 decimal place? 119.6 psi is the resultant pressure in a tire. or in a propane tank. That's maybe a better analogy, but 40 psi is more like a tire pressure, although high, but for a passenger vehicle it's too high, for a bus it's too low. So, but anyhow, think it through again. You start with a low temperature, temperature goes up. Oh, and it's Fahrenheit, not Celsius. Alright, so 12 degrees, it's pretty cold. So anyhow, you start with a low temperature, you end up with a higher temperature. Therefore, logic dictates that you start with a lower pressure, you must end up with a higher pressure, and that higher pressure will be 120 psi. I just rounded it to the nearest whole number. Okay, so I hope that sounds logical and that makes sense. Let's look at another one in metric where instead of pressure, temperature needs to be calculated. This is how the metric variant looks like. We have Celsius degrees and kilopascals. In conditions 1, we have 36 kilopascal pressure inside a pressure vessel with rigid walls and ideal gas. And pressure 2 is 5 kilopascal, so pressure drops down. Now the volume doesn't just collapse in the container, nobody opens it or whatever, it's the same gas in the same container, but the pressure drops down drastically. What causes it is a corresponding drop in temperature. So starting at 55, I expect temperature 2 to be a lot lower than the initial temperature because that corresponds to a lower pressure. That makes sense? I hope so. So pick an equation that you like, any one of them, replace the letters in them with the numbers that are given. 2 of them will line up on one of the diagonals, multiply those 2 numbers because they're interchangeable in any order, and divide by the third number. If you enter it in your calculator, this is what you're gonna get. If you round it to 1 decimal place, temperature 2 will be 7.6. So, to sum it up, or to have a reality check on this math, started with a higher pressure and a higher temperature, ended up with a lower pressure and a lower temperature. This is exactly what Guy-Lussac's law states explicitly, and this is what it's about. So that's how it works. That's what it relates to. Like I said, automotive or welding, aviation, tire pressures, whatever, are all potential fields where this is applicable, and this is how you do math with it. Thank you very much for watching.